Well, hello, everyone. In today's lecture, we're going to talk a little bit more about these standard potentials that we talked about last time, and in particular, some of the important applications of them. First thing we're going to talk about is the so-called Nernst equation. Now, you remember back when we talked about equilibrium and the connection between the Gibbs energy change and the equilibrium constant, when we spoke about the thermodynamics of the equilibrium constant, that delta G, the Gibbs energy change for a reaction, is equal to the standard Gibbs energy change, which means all components in their standard states, plus RT ln Q, where Q is that Q factor, as it's called, which is, of course, all of the products raised to their exponents multiplied by each other, divided by the same thing for the reactants. Now, the delta G we also found in the last lecture is equal to minus NFE, where E is the cell potential, and F is the Faraday constant, and N is the number of moles of electrons being transferred in each reaction. And under standard conditions, delta G0 is minus NFE0. So, putting these two equations together, we can say that the delta G here is minus NFE, which comes from this, and that's equal to minus NFE0, which is the delta G0 portion here, plus RT ln Q. Now, what this does is it connects, as you can see, the cell potential and standard cell potential with the Q factor, and hence with the equilibrium constant, as we'll see. So if you rearrange this, you see that E, the cell potential at whatever the concentrations and gas pressures are, equals the standard cell potential with all components in their standard states, minus RT over NF times ln Q, the natural log, which is the Nernst equation in its simplest form. Now, at equilibrium, of course, E equals 0 because delta G equals 0 at equilibrium. And at equilibrium, Q equals K. So in that sense, we've now connected the equilibrium constant to a cell potential, which is what the purpose of the Nernst equation is. So we can see then that E0 equals RT over NF times the natural log of K, which is also equal to delta G0 over NF. And the log of K then is NFE0 over RT, which is minus delta G0 over RT, which we already knew. Now, since the Faraday constant, F here, is 96,485 coulombs per mole, that comes about because the charge on one electron is 1.6 times 10 to the minus 19th. 1 mole of electrons then is that number times Avogadro's number, which is 96,485 coulombs per mole. Coulomb is a unit of charge. The gas constant R, even though no gases are involved, of course, is 8.314 joules per mole K. And if the temperature is 298, which is 25 C, and the natural log is converted into common log, log to the base 10, which is dividing the natural log by 2.303, that's the natural log of 10, then we can say that 2.303 times RT over F is 0.0592 volt. Therefore, the cell potential here is E0 here minus RT over NF, which is 0.0592 over N, times the common log of Q. And this is the reason for defining it this way is because years ago, the common log was more commonly used than the natural log. And so this just converts the natural log into the common log. Either one is okay, of course, depending on how the Nernst equation is applied. So that means that rearranging this a bit, we can see that the common log of the equilibrium constant is NE0 or 0.0592. And this is a useful relationship, as we'll see when we develop this a little bit further. Now, one of the features that it's useful to note is that when we talked previously about cell potentials involving two half cell potentials combined, where the overall cell potential was the half cell potential of the cathode reaction minus the half cell potential of the anode reaction, then the overall cell potential was given by that difference. Now, suppose instead that we have two half cells which involve the same reaction. This one is the reaction of copper to copper 2, or reversibly, copper 2 to copper. And so suppose that we set up an electrochemical cell like this that has the same half cell reaction in both half cells. They both involve an electrode of copper here and here, and they both involve a solution of, say, copper sulfate, which is blue. Now, as long as these two concentrations of copper 2 are the same, of course, the cell potential will be 0 because there is no driving force to go in either direction. But if the concentrations of the copper 2 in the two half cells are different, for example, in this half cell, it's 0.001 molar, 1 millimolar of copper 2, and the concentration of copper 2 in this other half cell is 1 molar, then there's a difference in the two concentrations. And so, as we know from the standpoint of entropy, combined with the equilibrium constant and the Gibbs energy, there will be a driving force for these two concentrations of copper 2 ions in solution to become equalized. In other words, the driving force, the preferential driving force, will be for the copper 2 concentration here to increase, and the copper 2 concentration here to decrease. Now, we can essentially say then that the overall cell is composed of two half cells that involve the same reaction, except one of them will go in a direction that increases the copper 2 concentration here, which means it will be the anode. Copper will be going to copper 2. And in this case, in the right-hand half cell, copper 2 will be going to copper. That decreases the copper 2 concentration. And so the result of this overall process is that, yes, copper 2 in this compartment will be increasing, which means this is the anode, because copper is being oxidized to copper 2. And this reaction here is occurring. Whereas in this other half cell, copper 2 is being reduced to copper metal. And so this will be the cathode compartment, because the anode involves oxidation and the cathode involves reduction. So how does the Nernst equation apply to this? Well, the net reaction, and I put reaction in quotation marks here, because in a sense it is a reaction, but it's the same thing on both sides. So it's not as if something is being transformed to a different element, but we can still refer to it as a reaction occurring in these two half cells. The overall reaction then is copper 2 in the cathode compartment going to copper, and copper in the anode compartment going to copper 2. Of course, the E0 for that reaction, so to speak, is 0, because there is no net change in the species. But according to the Nernst equation, we can set up an expression like this. The cell potential of this combination will be the E0, which of course is 0, minus 0.05916 over 2 times the common log of the ratio of these two copper 2 concentrations. The one in the anode, which is 0.001 molar, and the one in the cathode, which is 1 molar. So solving this, we get, of course, it's a 2-electron reaction, you can see. And so N is 2. And so the common log then of 0.001 over 1 times all of this is 0.089 volt. And in fact, if you were to set up an electrochemical cell involving these two half cells with these two initial concentrations of copper 2, you would observe a voltage of about 0.09 volt. And this is an example of what's referred to as a concentration cell. It's called that for obvious reasons, because what drives it is the fact that there are two different concentrations for the same reaction, essentially, one going as an oxidation and one going as a reduction. And so this idea of a concentration cell actually has some important uses. For example, if you have an iron pipe that's underground, and at one end of the iron pipe there's moisture, and the iron can in fact oxidize to iron 3, and at the other end iron 3 could reduce to iron 0. And so in effect what you would have along that pipe is what amounts to a long electrochemical cell. And so what this leads to is corrosion of the iron. It will cause more of the iron 0 to go to iron 3, which causes it to form rust. This is an important consideration in plumbing operations underground. Iron pipes are not used so much anymore, as you probably know, but this was an important effect when iron pipes were used, and they underwent a lot of corrosion for, at first, reasons unknown. Now, another example of the application of the Nernst equation and what is basically a concentration cell is a pH meter. Now, we're all familiar with what a pH meter is. It's a device for measuring the pH of a solution that is unknown, an unknown pH. Well, nowadays, pH electrodes are combined into one electrode. What's shown here is the old-fashioned one that involves 2 separate electrodes that complete a concentration cell. But the principle is the same. The modern ones that involve just one electrode combine both of these operations in the same electrode. So the chemistry is still the same. So what we have here is this. In one of the electrodes, there is and there are different ways of doing this, but one of the commonest ways is to have a silver chloride electrode, as it's called, that involves silver and silver chloride, and it operates as the cathode, where the silver chloride, which involves silver +1 and chloride -1, plus an electron goes to silver metal, so the silver is getting reduced. That's the cathode reaction. The chloride, of course, is unchanged, because chloride in this case is a spectator ion. Chloride is -1 here, and it's -1 over here, so nothing has changed as far as the chloride is concerned. Silver has become reduced. In this electrode, there is essentially a silver wire that's coated with silver chloride right down here, this portion here. In this little compartment here, this is the typo, by the way, this should be 1 molar HCl, not 0.1. In this little compartment here is exactly measured 1 molar concentration of HCl. And then the important part of this is that this little volume right here is composed of a special kind of glass. It's a very thin membrane that allows the passage of hydronium ions, H+ ions, into and out of here. Okay? And the hydronium ions that we're trying to measure are in this solution here, this yellow solution or whatever it is. So the concentration of the hydronium ions in here is known. It's exactly made by the manufacturer to be 1.000 molar. And so out here, it's an unknown. So you can see in effect that what we have here is a concentration cell with 2 different concentrations of hydronium ions, H+ or H3O+, if you wish. One in here, which is 1 molar, and one out here, which is unknown. So by measuring the voltage across this electrochemical cell, we can determine what this unknown H+ concentration is, as we'll see. The anode electrode is this. It involves, and there are various reactions that can be used for this as well, but this is one of the commonest ones. It involves what's called mercury calomel. Calomel is mercury 1 chloride. Mercury 1, you may remember from the last lecture, exists as a dimer. It's Hg2 + 2, and then chlorides. And so what happens in this case is mercury oxidizes to calomel. It incorporates 2 chlorides, which again are a spectator ion, and releases 2 electrons when it gets oxidized. And so what happens here, the way this is constructed is this. And this is a very clever design, as it turns out. There is a platinum wire, which serves as a conductor, but a non-reactant, of course. And in this little container right here, this little vessel inside, is a mixture of mercury and mercury calomel, Hg2Cl2, which is a solid. It looks like a kind of a cream-colored, metal-colored material. Now, there is a porous membrane at the bottom of this that allows passage of mercury ions and mercury atoms back and forth. In this portion of the electrode down here, there is a saturated KCl solution. All right, and so the thing that exists down here, as we'll see, is part of the salt bridge. Because it's a saturated KCl solution, there is a bit of KCl at the bottom here, which is what keeps the solution saturated. And in here, there is what used to be a small asbestos fiber. Nowadays, it uses something other than asbestos. It's essentially something that will convey the liquid back and forth. And this essentially is acting as a salt bridge. The concentration of potassium chloride up here is such that the transmission of ions back and forth through this asbestos fiber, it acts as a salt bridge between the saturated KCl solution. In that sense, it looks like this one right here, one of our standard salt bridges that we've talked about before. But it's playing that role by having a saturated KCl solution here, what would normally be inside of our U-tube shaped salt bridge. And then it acts as a conductor between this saturated KCl solution and our unknown solution. That's what completes the circuit. And so, in effect, what we have here is a concentration cell. We've got two different concentrations of hydronium, one in here that we don't know and would like to measure, and one inside of here, which we do know. It's exactly 1.000 molar. So the cell notation for this, and you'll have to excuse me, but this is written backwards. As I've said before, the standard cell notation is that the anode is on the left and the cathode is on the right, so that the reaction proceeds this way from left to right. But in fact, this one has been written backwards. The anode is over here and the cathode is over here. So we'll look at it going from right to left instead of left to right. So the anode, which is this electrode right here, right, consists of this mercury 1 combination, and it consists of this platinum wire right here dipping into that little mixture. And so what happens, the reason that there's a what looks like a metal surface, this vertical line here, is because it represents the surface of all those little bits of mercury metal that are in there, right? And so this is in contact with the saturated KCl solution. Then this double line is representing the salt bridge, which is this portion right here, okay? With whatever this little fiber is that connects the two. Like I said, it used to be asbestos. Nowadays, there are other things that are used instead. And then in here is the hydronium ion concentration that we don't know. This then is the glass membrane, which is the surface of this special glass that forms this little vessel here at the bottom of this electrode. That's the glass membrane, inside of which is 1 molar HCl. Okay? As I said, this is a typo here. This should be 1 molar. So the glass membrane serves as another surface like this. And then the AgCl and the silver, this vertical line here represents now the surface of the silver. So what we have is the silver is the surface of the silver wire, or whatever this is composed of here, going to the silver metal, and then the silver chloride which coats it. So this little vertical line here now is representing the surface of the silver. So this is the overall cell notation. It goes from right to left, which is incorrect, but that's the way it was written here by mistake. Now, the setup then with the Nernst equation to represent this is right here. Here's that E again. The E0 is 0 because it essentially involves the H plus the hydronium ion reaction in both directions. So the overall cell potential, the E0, is 0. And then here's our minus 0.05916. This is a 2-electron reaction, as you can see from the the mercury half cell right here, times the common log of the unknown concentration of H plus, that's in the solution, and the known concentration, both of which are squared because it's a 2-electron reaction, right? There are 2 H pluses that form when this conversion goes back and forth like that. So, of course, this is 1 down here, and 1 squared is just 1. So basically what we've got is this term right here times the common log of the square of the H plus concentration. Well, the square of that, since the 2 here will cancel the 2 here if we multiply this out, it's minus 0.05916 times the common log of the H plus concentration. Now, the H plus concentration, the minus the log of the H plus concentration is the pH, as we defined before. That's why this minus now becomes a plus. And so essentially the cell potential that's measured for this overall combination, right, between these 2 leads right here, cell potential that's measured is 0.05916 times the pH. So pH meters are essentially special purpose voltmeters, which measure this potential, and they're programmed so that whatever potential they measure is automatically divided by 0.05916 to give the pH correctly. And that's how these things can be used. This is another example of a concentration cell that is used to make a measurement of one unknown concentration versus one known concentration. Now, as I said, modern pH meters combine these 2 vessels into one single pH electrode, as it's called. We've already used some of those in the lab this semester, but this is the chemical principle that underlies them. So these are some, as an application of these cell potentials that we talked about last time, and in particular, the Nernst equation, which is a very important equation that is used to connect cell potentials and a thermodynamic quantity, which is delta G. And since it connects the cell potential and delta G connects with the equilibrium constant. So what we essentially have is a way of measuring an equilibrium constant by measuring a cell potential. And this is one of the reasons why the Nernst equation has such high applicability. Next time, we'll talk a little bit more about reactions that are occurring opposite to the spontaneous direction, so-called electrolysis reaction. So